Hey, Walter Sorrells back with more tips for the knife maker. Today, back with part 2 of our series about epoxy. So today I'm going to be testing a variety of epoxies, including some specialty epoxies and some affordable consumer epoxies that you can buy at big box stores like Home Depot or at your local hardware store. So right off the bat, I'm going to tell you that these tests are not big science here. At best, they're going to be kind of impressionistic. To really test these things rigorously, you need a good lab and, a lot of scientific equipment, and I don't have that. Basically, I'm just going into my garage and doing some testing. So I've done my best to do tests that will give you a glimpse into what to expect from epoxies, what they're good at and what they're not. But truthfully, I'm not here to give you product recommendations so much as to give you a hint of what the spectrum of epoxies will do and what you can reasonably expect generally out of epoxies. Knife makers tend to make knives that have pins driven through them and then epoxy beneath that. And I think a lot of guys would like to make knives that have no pins at all and that are just epoxied on. So we're going to kind of ask the question of how realistic that is. In simple terms, what I'm going to be doing here is attaching steel to micarta. So if you're new to knife making, you might not know anything about micarta, but micarta is basically a laminated material made from phenolic resin, and it's kind of a plastic-like material. By using micarta, we're going to be able to uniformly test materials that are the same in each one of these samples that we test. In simple terms, I'll be attaching steel to micarta and then seeing what it takes to knock it off. If you check manufacturer data sheets, you can find various measures of the qualities of epoxies: peel strength, tensile strength, shear strength, flexural modulus, and so on. Now those measures are all very good and well, but at the end of the day, all that matters to a knife maker is how well it holds up in knife making type applications. Here's the process. I've started by taking a number of pieces of high carbon steel, removing all the scale, and flattening them on a disc grinder. They're all precisely the same size. All surfaces were checked with a machinist's straight edge to make sure that they were very flat. And the micarta was trimmed to the exact size so that the surface area on all the test samples would be identical. Holes were drilled in the top of each piece of steel and in the bottom of each piece of micarta for test purposes. You'll see a second set of holes in each piece. These just happen to have been drilled in the scrap pieces, and because of their location and size, shouldn't affect the test results. They're the same on each one. Using the process outlined in part 1 of this video, the samples were prepped by degreasing, then scuffing with purple Scotch-Brite. More or less immediately, the various samples of epoxy were mixed and applied to the samples, which were then clamped using similar clamps along with a block intended to evenly distribute clamping pressure. The samples were then left in an ambient temperature of 70 degrees Fahrenheit to cure for several days. I tested 3 5-minute epoxies, one made by Loctite, one by DevCon, and one by JB Weld. I also tested 2 formulations of Blade Bond, specialty epoxies marketed for knife makers. I would have liked to have tested some more industrial type epoxies. DevCon, 3M, Loctite, West System, and many other brands are marketed into niche industrial markets, but they tend to be quite expensive and sold in large quantities. So yeah. Just didn't test anything like that. Now, all samples were left to cure long past their manufacturer recommended cure times, so curing shouldn't be an issue. All of them were mixed according to the manufacturer's directions. I begin by doing a little subjective test. scoring some of the squeeze out with a sharp tool just to get a good sense of the epoxy's character. Is it pliable, glassy, hard, chippy, whatever. After they'd sat around a couple of days, I honestly couldn't tell much difference between them. They were all pretty hard, but not brittle or glassy. Then the samples were hung, and then weights of increasing heaviness were hung from the samples to see if they would fail under a constant load. Check out that fancy scientific rig. I didn't anticipate any failure here. Samples were tested from 35 to 120 pounds of load. Given that these loads were about an order of magnitude under the reported shear strength, I would have been a little surprised if they had failed. And they didn't. Next, I dropped a 35-pound weight a distance of about a foot. This resulted in a transient spike of force of, hell, I don't know, a bunch. Again, no failures. Next, I applied force to the tip of the sample. This is basically a peel test. Again, I hung various amounts of weight on the end to test the static load. None of the samples failed under my peak load of 70 pounds. In fact, I actually bent several of the test blades. Next, I did a drop test. Again, peeling rather than shearing. This, frankly, was a poorly designed test. I changed the position of the samples in order to keep the load spike from being absorbed by bending the blade. But what ended up happening was that the weight just bounced off the sample. So there was a sudden spike of pressure on each sample, and then the weight bounced off. For all I know, this may have caused totally different amounts of pressure on the various samples. Anyway, whatever the case, the JB Weld failed on this test. So JB Weld done for the day. The others all passed. Final test. Least scientific, least rigorous, most abusive, and most susceptible to random error. Yeah, well, I said from the beginning here, I'm not a scientist with a big-ass lab and a $4 million government grant, am I? So, here's the test. You take the samples, and you throw them up in the air and you let them land on concrete. You want real world, that's real world. Now, I've done this with pinned handles on my own blades, and they've been able to sustain hundreds of impacts before the handles finally delaminated. Not these. Without handle pins to buffer them against those shearing forces, they all failed relatively quickly. DevCon failed on the 5th impact, Loctite failed on the 8th, the Blade Bond Ultra formula failed on impact 10, and the Blade Bond Edge 15 formula failed at impact 20. The winner is... Randomness aside, to me this is an interesting result. It suggests, if not very conclusively, first, that some epoxies are indeed superior to others for knife-making purposes. I don't think it's accidental that the Blade Bond blades survive longer than the epoxies you buy at Home Depot. Loctite and DevCon also sell high-end industrial epoxies with more neatly tailored working properties than these. It's in the nature of the hardware store type product that they're intended for general use. And frankly, on a pinned handle, I don't think you'd be sorry if you used them. But, by the same token, if you're trying to make the best possible knife, and that's kind of what the custom knife game's all about, you might be well served to go with epoxies that are aimed specifically at your application. Let's take a look at the steel and see how much micarta delaminated. In other words, did the bond fail or did the material fail? So here's the JB Weld sample. Here's Loctite. Here's DevCon. And here's Ultra, which I call BB1. Here's Edge 15, which I tagged as BB2. As you can see, this one held appreciably better with much more micarta still stuck to the steel. indicating that the material itself failed before the bond did, which is a pretty darn good result. Incidentally, if you're wondering if I've been compensated by Blade Bond to stack the deck in its favor, the answer is no. I got a couple bottles to test, and that's it. So here are some final points. First, these tests show nothing about how well any of these epoxies will hold up over time. It just shows what they do basically right out of the box. Also, it should be noted, and this is a point I made in the first of these epoxy videos, that mercaptan-based epoxies will not stand up to water as well as polyamine hardened epoxies. So especially with cooking knives, outdoor knives, survival knives, dive knives, anything that might run into really prolonged exposure to water, you'd be better off staying away from mercaptan-based products. A corollary to that, though, is that relatively impermeable materials like micarta, G10, and so forth are less likely to wick water into the bond than ones made from natural materials like bone and wood. Okay, so I really hate to disappoint you, but the bottom line here is if you're looking for me to tell you to go out and buy such and such epoxy, it's the bomb, everything else is crap, I'm not going to do that. But hopefully you've gotten enough information here to make some pretty good decisions. Also, this may give you some thoughts about how to conduct some tests for yourself. So irrespective of the fact that some famous knife maker may say, oh, this is the way I do it, it's really important for all of us to go into our shops and test out materials for ourselves. Test things to destruction, see how they really work. So that doesn't mean that there aren't any takeaways here. First, what these tests tell me is that if you properly apply commercial consumer epoxies to bond handle scales to handles, and you use pins or screws, fasteners like that, you're probably going to have a pretty solid bond that's going to last a good while. And to me, that's actually a pretty encouraging thing to know. So the flip side of that to me is I'm not going to be going out and making any pinless handles anytime soon. It just seems like the evidence here would show that they're too likely to fail under hard use. So I'm just not going to be doing that. Thanks for watching. Hope you enjoyed this video. If you liked it, here are a couple of other videos that you might be interested in. Also, like me on Facebook at Walter Sorrells Blades, and check out my website, waltersorrellsblades.com, where you'll find examples of my work along with instructional videos showing all aspects of Japanese sword making, including forging and polishing, how to make hamones, and how to make fittings, scabbards, and handles for Japanese swords.